Welcome back to the Automation Podcast. My name is Shawn, and today on the show, I meet up with Chris Novak from HBK to learn about the technology behind strain gauge load sensors.
Chris, thank you for coming on the Automation Podcast. I'm really looking forward to your presentation talking about strain gauges and how they're used in automation and how they work. I think a lot of our audience have used them in the past, but may not know all the technical pieces about it. And they may also like to learn about what your company has to offer in this area as well. But before we get into all of that, would you take a minute to kind of introduce yourself to our audience?
Yeah, I'd love to, Shawn. Well, first of all, I want to thank you for having me on, and I'm looking forward to today's session here, just talking a little bit about, like I said, strain gauges and giving an overview, background, a little bit of educational of, how strain gauge sensors really work, what they're all about, and how they can be utilized in the automation world. So background, a little bit about me. I basically have a bachelor's degree in electrical engineering from Cleveland State University. I'm currently a business development manager with HBK, but I've been in the test and measurement and sensors world for, basically my whole career, 25 plus years of experience doing really more of the mechanical hardware side of physical measurement testing, into the manufacturing side of physical measurement where sensors are utilized, force sensors, as well as, I handle a lot of other sensors in former lives of torque sensors, as well as displacement and pressure and things like that. But for today's purpose, we're going to focus on a strain gauge and really a strain gauge force sensor. So with that, maybe we can go ahead and get started, talk a little bit here. So, what is force? What is it? What is it really? And, by definition, basically a force is, a push or a pull upon an object resulting from the object's interaction with another object. So whenever there's an interaction between two objects, there's going to be a force upon each of those objects. And forces only exist really as a result of this interaction. If we look more from the engineering side, what is the definition or what is really the equation and formula all about it? Well, force is mass times acceleration. And in the English world, for us, it's pounds force. And in the metric or SI world, it's really, referenced as newtons. And by definition, a newton is the amount of force required to give a kilogram mass of acceleration over 1 meter second squared. So 1 newton equals 1 kilogram meter second squared. So really, what does that really mean? Well, again, for mass, we have defined SI unit as being a kilogram. And for the US, the pounds, basically mass is represented as pounds mass. And mass is really a constant property of an object. When it becomes the force, basically you could think of it as weight. And weight is really the interaction where gravity is involved rather than a push or pull for force. So again, the newton is kilogram meter second squared. The unfortunate thing in the U.S. world is you have that same reference point of mass equal to pounds, but then you also have your pounds of force represented with the same terminology. Really, the only thing you need to think about there, though, is weight can vary with gravitational pull, where mass is really just a constant object. So where does that come into play? Well, that leads into my next slide here. A lot of times you'll hear terminologies of load cells and force sensors. And a lot of times they are referenced, a force sensor is being referenced as a load cell. And, that is true. The designs are very close. And especially when you come to strain gauge sensors, they're designed, as we get into this, you'll see, they're designed very similar, but there are some distinct differences. A load cell, really is designed to be acted upon by gravity. It's usually designed for weighing something, scales, So really, if you think about it, am I doing an actual force or am I actually trying to weigh something? So that's a lot of big distinguishing where in reality, you should be thinking load cell for weighing, force sensors for everything else. So a force sensor, although similar in design, they're not designed specifically for gravitational use. They're designed to be utilized in forces in any direction, not relevant to the actual Earth's gravitational pull or force. So a little bit distinguished there between the two types of sensors.
Yeah, I think a lot of us have seen load cells in action, weighing materials that are going
Yep.
into a batch. But also, I think of the times where you're looking at stress tests on different components and where they're using force sensors to measure, how much am I pulling the two ends of this material apart? I got to measure how much force is being put on there before it breaks. So I know, when that happens. And I can think of other applications where the force isn't strictly down based on gravity. So
Exactly. Yeah.
that was
Yeah.
a very good way of explaining it. Thank you.
Yeah, I mean, you think of actuators pushing or pulling on something, right? And a couple
Exactly.
slides down the road here, I get into talking a little bit more about the applications and a little bit more of an overview on there. But exactly, there's that little bit of distinguish whether you're trying to actually weigh something where gravitational force is the interacting aspect on the object, or is it a push-pull being, derived from some other means in your mechanical system? Yeah. So before we actually get into the actual and lead into the bonded foil strain gauge and strain gauge sensors, I thought I'd do a quick little educational, just what are some of the other sensor technologies out there, just to give a little bit flavor to the audience. There's sensors out there that are designed what we call without a spring body, or what we really mean there are changes are due to electrical properties only. And these are technologies like magnetoresistive, your Hall effect, or piezoelectrical type scenarios. Then there's, a batch of technologies that you really use as force compensation or comparator. You can think of this as magnetic generated forces, electromagneto or magnetoelastic type effects. And then we come into those that what we call utilize a spring body or where we're doing strain detection on the surface of materials.
Before we get to that, I have a special announcement. I've just released my very first book. It's an ebook and it's entitled Logic's Book of Knowledge. What I did is I combined all my Control Logix articles from the last 10 years into an ebook. I updated them, I added new pictures, and I made it all available for just $9.99. So if you appreciate what I'm doing, if you want to support the show and the channel and the blog, then please check out my brand new ebook, Logic's Book of Knowledge, which you can get over at theautomationblog.com/BOK1.
And there's really two main types of technologies utilized out there for sensors today. One is surface acoustic wave or SAW technology, and the other is really your strain gauge technology, your bonded foil or semiconductor strain gauges that's been around, for years now. Basically the foil strain gauges, came about really back in the 1950s. So it's a true and proven type of technology that people rely on to be able to design sensors that are very accurate, very repeatable, very trustworthy, improving in the industry. So getting into a little bit further, and I'm not going to get deep into this, but I thought I'd give a little bit of a technical overview of, some of the formulas or properties or interaction of what really utilizes the tools or the background between making up strain gauge utilization and the strain gauge force sensors in general. And that revolves around Hooke's law and Young's modulus in particular, that basically a material will have an elasticity to it, based on Young's modulus. And basically that stress is really the relationship or the coefficient of Young's modulus tied to the strain level. So when you interact on a material, it's going to change or deform somewhat in an elastic type manner. So as you pull something, think of it as almost a spring loading and unloading. That's what's going to take place with a strain gauge type sensor with the strain gauges themselves, as well as the body or the element designed around the sensor, and we're going to get into that a little later. I'll show you a little bit more specifics on that. But it's an interaction of stress to strain where you reach a certain elasticity point and you relieve that, it's going to bounce back. So almost like a spring effect. But if you reach too high of a stress level or you apply too much strain, you then break that limit of elasticity of the material properties of both the strain gauge and or the material that the strain gauge may be bonded to. And then you'll yield or deform the actual sensor or material itself. So that quick little overview, just a little bit of background to, put on our thinking hats of some of our engineering, formulas and principles and how these really come into play in real life then.
Yeah, I don't know if it's only me, but I remember as a kid playing with the slinky, and then
Yep.
you stretch it too far and it doesn't go back. So.
Yeah, exactly. It becomes damage, right? Oh man, there it goes. Yep, exactly. Or you think about a little bit like almost like a little bit of a paper clip, right? If you a paper clip actually spring action, right? But if you unload it or put too many papers in a paper clip, it deforms and doesn't come back to that original state. That's the material actually bended or pulled beyond its elastic capabilities, really. Yep.
Excellent.
So here we go here. Just a quick little overview of really what is the strain gauge and, kind of what it looks like. In simple terms, a strain gauge is really like a long grid of wire or a piece of foil, a solid, length. And what we do is we encapsulate that or put coverings around that so that we can utilize that to be bonded to the actual structure or material. In this case, we're going to be talking about bonding it to a spring body to make a sensor. But strain gauges are, there's a lot of different variations, sizes, and capabilities, that are designed for a lot of different material stress analysis, besides just building and force sensors, again, so the two main purposes for bonded foil strain gauges. One is for truly stress analysis, where you bound it directly to a piece of material for analytical purposes, and monitoring stresses on materials. And the other is using strain gauges to actually build a sensor to be utilized in the physical measurement or test world. Okay. So really what it boils down to is when, metal will elongate and it'll get longer and thinner, and the resistance will actually increase in a strain gauge as you basically deform it or pull it or tension it, and we'll get into a little bit more of that, and I'll show you a little bit more specifics on that as we go along. So, what is a sensor? How does it really work? Well, here's a quick little overview of some of the main components that we kind of were alluding to a little bit before. So first you have basically a structure, what we'll call the element spring body. And then you basically, if a force is introduced on that surface of that material, and then we bond that strain gauge to that area, it's going to deform and it's going to change the characteristics of not only the strain gauge or its resistance, but it's going to be changing or straining that spring element to deform and bounce back. And then what we do is we utilize an electrical circuit that's called a Wheatstone bridge, where we wire up the actual strain gauges in a unique way to form this Wheatstone bridge, so that when you are powering an electrical circuit and the strain gauges are deformed, it's going to unbalance this Wheatstone bridge and give you an electrical output that's directly related to the spring body force that you're actually interacting or pushing and pulling on. And I got a slide here that'll get a little bit more into details there. Go ahead.
Okay, great. No, I was going to say, does the resistance, because the film is being deformed, does it change the resistance of it?
Oh, exactly. That's exactly what's happening. And you'll see, I think in this next slide, I get into a little more specifics on that, and you can actually see how that all interaction and how this little component parts of the spring body, the strain gauge, the Wheatstone bridge all come together to really form this overall strain gauge sensor. So really what you got is a mechanical, element, that is a structure that performs in a predictable and repeatable manner, right? So you're going to have a slight deflection when you apply a force. And then this force is actually going to be translated, into this electrical output through the use of the strain gauges that are bonded on that surface. So basically, you basically are applying, a force. It's translated into an electrical circuit through this Wheatstone bridge. And typically you'll have 4 active gauges, so we'll distribute the gauges on this element so that when you're pushing or pulling, you're going to have, like you said, the change in resistance, where some of the gauges may go into a compression mode. So if you look in the center here, basically without any load and a strain gauge bonded to a specific surface, you have a fixed length and height. When you apply a positive strain or you pull or tension it, it's going to become longer and shorter, and the resistance is going to increase. When you compress it, you're going to basically have it become shorter and thicker, and you're going to get a negative strain or a negative resistance. So by uniquely distributing these strain gauges on the material, you basically are going to form this Wheatstone bridge where some resistance is going to increase, some is going to decrease, so that you'll get this change in resistance to actually give you an electrical output that's going to be directly proportional to the physical push and pull or forces that are being applied to that element. Okay, so it's a unique way where everything comes together, where you transform the mechanical to an electrical in a repeatable, predictable, and accurate means. Okay, so for example, in this Wheatstone bridge, when you have it wired up and you have a sensor sitting there, you have what's called a balanced Wheatstone bridge. You apply a fixed input voltage, and with nothing acting on it, you would have a balanced bridge. You would have no output. But now when you start putting a force on there, you're going to change the resistance. It's going to unbalance this bridge and give you a deformed electrical output, or give you an output of voltage that's directly related to that force. Now, with this being said, that output is a very, very small, electrical output. It's in the millivolt range. And if you may recall, HBK kind of hosted, a little bit of podcast with you where we talked a little bit about signal conditioning and strain gauge amplifiers. And this is where it's important to where the raw strain gauge bridge itself, usually because of that small millivolt per volt output, is tied to a signal conditioning of some sort to give you a more robust voltage or current output, or maybe tie it to a digital display, or maybe even tie it to a PLC or other aspects into the system. Okay.
Yeah, a lot of PLCs do have millivolt input modules, but those signals don't go very far. They're obviously, since it's very low voltage, is affected by the distance of the cable, because the cable has its own resistance, right?
Yep, so exactly.
Converting it to 4 to 20 is typically a very good thing to do. Even a lot of 0 to 10s are converted to 4 to 20 just to get that extra distance and robustness there. So
exactly, yeah. And we're also seeing a lot of that being translated into the digital domain now, right? So where you basically digitize, right there, and send a digital type signal, of a higher, 24, 32-bit A-to-D converters and things like that are utilized, and you'll see that as well.
Yeah.
So moving along, the bonded foil strain gauge are an important tool utilized with the sensor, but the actual main critical component is the actual spring body, how you design that particular element so that you will get a predictable and repeatable type measurement, right? So the function of this structure is basically to serve as a reaction force to this applied mechanical load or force that you're applying to the sensor, and basically focus, this load that you're putting onto this object to an isolated uniform strain field. And this is where we design or try to determine then within that spring element, what is the best and most strategic place to put the strain gauges, to get this accurate and repeatable and high accuracy type measurement. Okay. So with that said, there's basically a couple different designs that are utilized or ways that the spring elements are designed. And one is what we call a column or a bar style. And this could be a single column where basically we're necking down an area of a column and laying the strain gauges for a push-pull, tension, and compression, or sometimes a multi-beam where you're actually putting multiple beams and we're putting strain gauges on each leg of a multi-beam type scenario. And this is something like our HBK C6B type sensors utilize this, column or bar style type technology. And then there's probably one of the more types of designs, which is just a single bending beam, or sometimes what we call a double bending beam, where really you're just laying strain gauges on a beam and looking at the lever approach of the flexion of a push or pull force being acted upon on that sensor. So you'll see this design used a lot with actual load cells, a lot of single point load cells, shear beam type load cells, where you're just doing a push pull through a bending beam design. And one of the S style that, HBK utilizes is our HBK S9M type style for this design. And then we have what's called a diaphragm or a membrane style, to where we're actually laying strain gauges on an actual uniform diaphragm, or almost like a cylindrical type, not a beam itself, but more of a diaphragm, and this is usually utilized a lot in the miniature style of sensors. So miniature tension and compression, or miniature button style load cells, for example, our HBK U9C or C9C type products, very compact, where basically the deflection of a small membrane where the strain gauges are bonded is interacting with that push-pull type mechanism. And then lastly, and probably the most popular these days, is what we call a shear web design, to where it's like a bending beam where you're doing the push and pull up and down, but the internal beams are a little bit more thicker, more robust, and we're actually laying a strain gauge on a 45-degree angle, so that we're monitoring really the shear of the push and pull of tension and compression on the gauge. And what this does is it allows us to get very large capacities at very accurately with minimal deflection. So things like side loading and bending moments could be mitigated through this design of using the shear web, because it doesn't have crosstalk error as much as a bending beam style or the membrane style, where the interaction of off-axis loading will compromise the actual true inline push or pull that you want to really measure. Okay, so this shear beam design has become a very popular design in the world, and from the HBK world, it's basically our U10 series, or one of the more popular models, our U10M specifically.
Yeah, I think I can. One thing that's in common of everything that we have on the screen right now for the audio audience is that all of these designs have focused on a center point where the load is going to be, or the force is going to be applied. So whether it has a hole or a cylinder, it seems like. Would you say that would be the case with most strain gauges?
Oh yeah. So for example, looking at
center point.
Yep. Looking at a couple of these examples. So some of them could be like on the far left, this C6B. You may have a bolt pattern, maybe a flange to mount to on top and bottom, but you're physically going to be putting these sensors in line with the push-pull action, right? So it's how do you mechanically, and that's actually going to lead me right into my next slide, but I'll touch base a little bit here before I change slides. But you could have, a flange mount type thing. You could have female threads where you're mounting on the top and the bottom. Or from a compression standpoint, you have a little button radius where you're just putting on the top center and pushing on that through the means, or maybe a male thread on the top and bottom. So some of our miniatures, you'll have a male thread to connect to on the top and a male thread to connect to on the bottom. Sometimes you'll see a male on the top, a female on the bottom. So a lot of different mechanical interfaces, but usually that interaction is going to be that push-pull through the primary axis, or what we call the F sub Z axis of that push and pull orientation. So no matter where you turn your sensor, but you're thinking of it as loading and unloading through that center line, exactly like what you said, Shawn.
I was just going to say, I see that the button types look very, and the threaded types look very obvious. But if we go back over to the C6B,
yep.
Are you saying that I would have in this case, a 6-hole flange that would mount to the
yep.
top of that?
Yep, and you can't really see it in the design, but in the very center, the ring, there's a little lip there, right? So a lot of times you'll have this embossed raised area to use for centering, okay? So then you basically, when you bolt that up, you basically are concentrically aligning these sensors. So again, the ideal thing is you want to load right down the center line of that sensor, right? So having that little embossment and using that as a guide when you're building your adapter fixtures helps center everything and keep everything true down that center line. So the precision of machining from a mechanical piece becomes very, very tight tolerancing. I mean, sometimes we're talking, 5-10 thou of alignment for center and concentricity and centering of the sensors. So doing a flange mount sometimes is a lot more involved than maybe just having a simple thread down the center line or having a button style type sensor. Okay.
Makes a lot of sense.
Yeah. So what does this all mean? Well, through these different designs, we can have a multitude of different mechanical configurations like we were just talking about, from small sensors to very, very large sensors. I mean, we've done sensors that have gone into, 10 meganewton type loading frames. Think of the, large applications for like Navy and Marine where you're doing structural integrity testings of a ship hull, right? Where you got very, very large forces, deforming, the beams and the hulls of the ship. And you want to basically, define or understand that material composition and what forces it takes to deform and things like that. So a lot of different mechanical configurations shown here, kind of different modes of operation. So you have what's called sometimes compression only. And this is where you're just taking an object, you're putting in a line and you're compressing it or squeezing, the unit. And then you have what's called tension or tension only. You could think of this as maybe like a cable pull, where you're just trying to pull an object apart. That would be a tension mode. And then, of course, there's both your tension and compression, where you're doing a push and a pull in conjunction, maybe crossing through zero, going from a full tension mode to a compression mode. Again, think of maybe an inline hydraulic actuator or a piston going up and down, where you're basically, going to be going through both a compression and a tension mode of operation, or a push or pull forces in both directions. Okay, so a multitude of different mechanical configurations, all utilizing that 3 or 4 core designs. So depending on what your application, depending on what your requirements are, whether it's accuracy, whether it's size package, whether it's environmental, whether it be your mounting configurations, we'll build a multitude of different, configurations to best fit you and utilize it in how you want to basically be utilizing the product. So here, it basically just a typical layout. So again, typically you'll have a bonded foil mechanical piece of sensor that'll interface through a connecting cable to some sort of signal conditioning. So here again, shown as the HBK ClipX, which we talked about in the past on one of your podcasts, how that amplifier could be utilized, into the automation world, but maybe doing some higher end math channels. But in the end, a lot of times this will be fed to a PLC or maybe to a data recorder or a logger or something like that. So this is a typical, layout where you have sensor, instrument tied to some sort of a controlling or monitoring device of some sort. Now, a lot of times what we're also seeing, like I talked about, is maybe we're going away from need of doing the actual external signal conditioning. Let's say you just want to interface the sensor directly to your PLC or something. You could have a built-in amplifier directly on board the sensor, and just to give you that higher level voltage or a current. A lot of times more in the manufacturing automation side, you'll utilize that 4 to 20 output, right? So we'll just build a small little signal conditioner embedded actually into the sensor, and then run basically that higher level current directly to where you could run that to your PLC, your controller, or your data logger. Okay. So what does this really mean? Why would we incorporate force sensors as part of our system? Why does it become part of our measurement chain? Well, it could be for a multitude of reasons, and here listed are a couple bullet points, for product optimization, for product performance and validation, for doing functional test or end-of-line testing, for basically monitoring and controlling production processes, ensuring, the quality of a product. So knowing, and having certain tolerance bands set around the product process, you basically set up a go, no-go scenario, or weed out some of your bad product versus the best, or maybe grade your product based on how good it is with, force sensors becoming part of that feedback loop into your system. And lastly, a lot of times they can be utilized for preventative maintenance. If you've got $1 million production machines, you want sensors on there that become the eyes of that machine to allow you to maybe have a control stop before a machine goes too far to become damaged, right? So, sometimes you could think of sensors becoming the eyes and ears of your actual production line or assembly by giving you that feedback loop, besides just giving you, data that can maybe optimize your process or control as well. So a couple other areas just to think about from an application standpoint, 2 buckets you could think of: metal forming, press system operations, or you could think of assembly lines where you're doing press fit, again, functional or end of line final type testings. You'll see a lot of this into the things like riveting machines, clinching, fastening processes, all these could utilize force sensors and sometimes displacement to give you that real-time monitoring and control during your production process. They could be used in numerous of other tier automotive type companies where, that feedback of the steering systems or your tie rod assemblies, and probably one of the a unique weird one or unusual one, I should say, is, we did an application where we actually were instrumenting load cells during the production line for manufacturing of cork for wineries, right? Having that quality, again, control to, a predetermined length of a cork, but knowing the weight of that cork, gave them valuable insight of the density, the porousness of that cork, where they were grading corks and being able to, these winemakers making sure that they're going to be using the cork into an optimal means when they're producing their wine and basically putting it out to reduce scrap. You don't want a cork that maybe, of the wrong density to where it's more porous and allows the wine to become sour, or, maybe a cracked cork or something like that, or a chipped portion, so quality control, optimization of that could be utilized. So that was an oddball one, but again, force or load cells being utilized to help, reduce scrap and optimize your output or yield levels.
Yeah, I can definitely remember applications where you needed to apply a certain amount of force. You think presses
Yep.
and all that, too much force and it deforms or destroys the product. Too little and it doesn't stay together. It doesn't, you don't get that, just like a torque wrench on when you're working on your car. You have to give it the right amount of pressure for it to stay together, for the product to be formed correctly. But if you give it too much, then it's defective or brittle or, comes apart. So definitely makes sense.
Exactly. It becomes sort of like that spring body we talked about, where you reach that yield point, right? You release, you reach that point where it's beyond that elasticity point. And that's where force sensors can give you that determination before you get to that level of degree of deformation. Yep. And then, last couple slides here, just to, again, getting to a little more specifics of an application. Here's a good one I think everyone can relate to. Basically, a car body joining punch pressing, basically a cinching type process, to where we're utilizing force sensors and displacement to set up basically this go, no-go scenario during different processes of joining two dissimilar metals together to form a good bond, right? So basically, again, they were setting up with the force and displacement to give you these high tolerance band settings. And at first, you basically can see this no-go section. You would think, well, yeah, no, it looks like that's within your boundary lines or your upper and lower limits. Well, yes and no. It wasn't until they really looked into doing repetitive monitoring and traces to where they were basically able to optimize their particular assembly line, to where they knew not only when in the dead center here of when a good part was going through a go, no go, but they were able to use this to do some predictive maintenance of when a machine or part of their tooling, their cinching the tools, were becoming damaged or deformed. Basically when the load started becoming too high in force, then maybe the plunger, was becoming deformed to where you're seeing higher forces. Let's say if you started seeing a hairline crack in the tool, basically your forces started becoming lower, so basically they were able to use this as a predictive maintenance of when they needed to replace out their tooling, before they started producing scrap and had to redo the whole joining process on vehicles. So it gave them some of that insight. And lastly, with the lower forces, before the actual tooling would crack, you would want to monitor that to be able to actually shut down, maybe the assembly line when it hit too low, so that you don't damage the whole machine itself. Again, millions of dollars worth of preventative maintenance by having that control feedback. So this is, again, a perfect example how, force feedback into an automation process could not only just, produce higher quality, but avoid possible, downtime and damage that may happen to your overall systems.
Yeah, that makes a lot of sense, because you're not only here checking to make sure you're applying the appropriate force to cinch the two parts, right, to crimp them together. You're also, you can see over time if nothing else changes on the machine, but now the plunger's getting too big or too small, or the anvil starts deforming, getting defective. Then you can start seeing these waveforms, the measured values change.
Exactly.
And that's a great predictive maintenance type of scenario. So great example there. Thank you.
Yep. And I think with that, basically it rounds it out, saying, this is, again, a lot of different mechanical configurations, but, the strain gauge force sensors can be utilized in the automation world and are many, many times over for just about anything where you want to have, a little bit more insight on push-pull, interaction of your machinery, really, right? Or your production processes, or even from an R&D standpoint. Maybe before you go into a production means you want to maybe revalidate some things and do some pre-R&D testings, or limitations before you actually go into full-blown production. Yeah.
Well, that's excellent. And if somebody out there is either using a strain gauge and they're not happy with it, or they have a new application that requires a different type of strain gauge, or they need some help picking out a strain gauge, how do they find out more about what HBK has to offer?
So basically right up here, www.hbm.com, we have our full-blown website. There's all kinds of, different application scenarios. We also have other technical articles. We have some webinars that are on demand that also talk about a lot of this. And of course, there's an online downloadable application form where basically you can fill out a little bit of what your requirements are. And one of our sales guys or myself would reach out to you guys and be happy to work with you and provide what is the best solution to overcome what you guys are looking at trying to accomplish. So we'd love to, entertain and see how we can assist or support you in any of your endeavors or applications. Yeah.
Excellent. That's great. And for the audio audience, I know we keep saying the company name is HBK, but the website is HBM. So think of that as the brand name now.
Exactly.
Yeah,
unfortunately.
Yep. With that said, I really just want to thank you for coming on the show, Christopher, and telling us all about this, kind of running through the theory and talking about some of the products and applications. It's definitely something we haven't covered before, and I think it's a great follow-up to our earlier podcast about the clip backs and about the signal conditioners. So really appreciate taking time out of your busy schedule to come on the show. Thank you so much.
Oh, I loved it. Anytime. And be welcome to come back and get into more specifics or maybe even different types of sensors, because, we can look at different, pressure sensors or torque sensors, and a lot of those are utilized in the automation world as well. I'd be happy to go into more specifics along those product lines as well. Anytime. Thanks.
Well, I hope you enjoyed that episode, and I want to thank Chris for taking time out of his busy schedule to come on the show and bring us up to speed on the technology that goes into creating strain gauges. With that said, if you did enjoy this episode, please give us a like and a sub. And if you know anybody looking for PLC HMI or SCADA training, please send them over to my website, theautomationschool.com. And if you want to follow me or get in touch, you can always do so over at automation.locals.com. That said, I want to thank you all for watching today, and I want to wish you all a very happy, safe, and healthy week. And until next time, my friends, peace.